Good day, I am Lipardo, and now let's jump to propositional calculus. But first, let's define what a proposition is. A proposition is a complete either true or false declarative sentence. An example of a proposition is 1 plus 1 equals 2 or I am a human, because they are both either true or false declarative sentences. Meanwhile, the statement give this to Adam is not a proposition because it is not a declarative sentence. Propositional calculus, also known as propositional logic or sentential logic, is a branch of mathematical logic that studies the logical patterns or relationships between propositions or statements that can be either true or false. If a proposition P is true, it is denoted by capital P, while if its truth value is false, it is denoted by capital F. If there are two propositions that are connected by propositional connectives, it is a compound proposition. There are three types of compound propositions: tautology, contradiction, and contingency. If the compound proposition is always true, it is a tautology. If it is always false, it is a contradiction, while neither tautology nor a contradiction is a contingency. But first, let's dig deep into what a propositional connective is. A propositional connective is an operation that combines two statements to produce a new proposition whose truth value depends only on the truth values of the original two propositions. Conjunction, disjunction, exclusive or, implication, and biconditional are some examples of propositional connectives. If you combine all the knowledge we've learned just now, you can form a truth table. Let's create a truth table for the proposition the quantity of not P or Q and not R. First, we will use P and Q to construct the truth table. As you can see, the first column P has 4 T's followed by 4 F's. On the Q column, there are alternating 2 T's and 2 F's. And on the R column, T and F are alternating. Now we need to negate the columns P and R as required on the proposition. In short, all T's will become F's and vice versa. Now we find the truth values of column not P and Q first because they are contained in a parenthesis. By the definition of disjunction, the statement is true if one is true, and lastly, we find the truth values of not P or Q and not R, which is our proposition. Thus, our last column, by the definition of a conjunction, the statement is true if both of them are true, and we are done. We've constructed the truth value or table for the statement the quantity of not P or Q and not R. Now that we've established a truth table, let's jump to bit operations. Bit is a short for binary digit, which consists of zeros and ones. As customarily done, 1 will be used to represent P and 0 will be used to represent F. As you can see on first table, the first operation, or, if either the first or second bit is 1, the result is 1. If no bits are 1, then the result is 0. On the bit operation end, if the first and second bit is 1, the result is 1. It is important that both bit is 1 for it to have a result of 1. And finally, in the bit operation XOR, the output is 1 if the two bits are different, and 0 if they are identical, such as both zeros or ones. Additionally, a bit string comprises 0 or more bits. The length of this string is equal to its bit count. For example, 1010011000 has a bit string length of 9. Implications are also an important part of propositional calculus. In an implication, if the form if P then Q, the proposition is called the hypothesis, and the proposition Q is called the conclusion. If that whole form is negated, if not P then not Q, it is now called an inverse. Meanwhile, if the first form is switched, if Q then P, then it is called a converse, while a negated converse statement, if not Q then not P, is called a contrapositive. Let's now jump into propositional functions. A propositional function is a complete declarative sentence, P of x, that makes a statement about the variable x. The variable x is called the argument of P of x. And that's all for propositional calculus. Thank you.